Recording is rolling. It is Tuesday, October 24th. Right, so I'm covering up some AP details. Don't worry about AP. So you guys were just solving textbook puzzles today. The textbook puzzles today, um, look for a quiz by Friday and do some other stuff I want you guys to do with you guys later this week, including that turntable friction lab. So we're eventually getting that. But let's talk about some textbook puzzles. Okay, so as long as you guys are following along with me, then at the end of the week I will check that you guys have solved all these. You can either write these on separate paper. If you want to write these in your notebook, you can. Just show me your notebook at the end of the week, and then I'll put the points into these. All right. So now there are basically two categories of questions. Some of these questions are like the centripetal force, circular motion type question that we did the other day. Some of these are gravitation questions. Now, I was looking through your book, and I saw a lot of gravitation, but not a lot of circular motion for some reason. So here, let's do another circular motion question, and then we'll hit some of the gravitation eventually. All right, so the circular motion, these ones that are in gray. So I'm flipping over to the backside. Okay. Looks like there's 6 questions here that are circular motion. So okay, let's try number 1. Let's see what this is about. This looks fun. 1892, George W.G. Ferris, designed a carnival ride in the shape of a large wheel. I wonder if this became a Ferris wheel. This Ferris wheel had a diameter of 76 meters and completed one revolution every 20 minutes. Calculate the magnitude of centripetal acceleration and speed of one of the cars, which were located at the circumference of the wheel. Okay, so draw this out here. Draw this out. So number 1. Got a big old wheel going. Okay, they got like a base. They got like all these cars that are around, going around the outside like this, something like this. Okay. And okay, so it said diameter. Here, I'll spell it. So given. Okay, so diameter equals 76 meters, and one revolution to I'll say time period. Time period equals 20 minutes. What do they want us to find? So find says centripetal acceleration, so a sub c, centripetal acceleration, of course, and also the speed. Here, guys, aren't there actually 2 different kinds of speed? So v isn't that like a linear speed, tangential speed? Right. There's also an angular speed. So let's go ahead and find that too. We'll find that. So we'll find all 3 of those things. All right, you guys get that? Yeah. All right. So I know on all those equations that we've been working with, they don't really have anything in terms of diameter. I do have it in terms of radius. So guys, what would the radius of this wheel be? How do you go from diameter to radius? Divide by 2. Yeah. Okay, so 38 meters, is that okay? Okay. Gonna go over to this radius right here. Say this radius r equals 38 meters. Here's your radius right there. 38 meters. Okay, so that could be helpful. Let's see. Now time period is in minutes. Well, I know in all the guys, what's the base SI unit for time? Seconds. Right. So if I just want to pop all the numbers in the calculator and get a reasonable answer, I should really have the time in seconds, shouldn't I? Right. So I'm gonna say capital T for time period equal 20 minutes. Okay. But let's push it through some railroad tracks. It's how many minutes or how many seconds in a minute? 60. Does the number 60 go top or bottom? 60 seconds and 1 minute. Yeah. All right, and let's see, 2 times 6 is 12, and then 0 is 0. So the time period is that many seconds. Okay, that's equivalent to the time period in minutes, just in terms of seconds. Yes, that's a unit, right? Right, so now I think we can do some equations. And this does kind of remind me of this one right here. Guys from this one? All right. Or now this omega is your angular speed, so like turns per time, radians per second. Okay. And here's also circular motion, but this is in terms of a linear speed, I guess. It'd be. Okay. Oh, I got centripetal acceleration there. Right. So I think there might be different ways to navigate this. But if I know the radius and I know the time period of one revolution, let's do it this way. Or actually, maybe I'll ask you guys. What do you guys think we should do next? Our ultimate goal is to find these three things. Okay? I can think of some ways to do it. What do you guys think? What could be a good next step? Hmm. There's probably a few things we could do. Make some headway. So we know these things so far. We're aiming for these three things. Okay. Show you guys some formulas. All right, I have these formulas in terms of angular speed. I have these formulas in terms of linear speed. Yeah, these are hanging up on my back of my room back there too. Let's see this. Hmm. Hmm. Well, somebody come up with a good idea. Maybe I can't answer these questions right away, but maybe I could find something else first that could eventually lead that.
Yeah.
Hmm. Fair. I'll give you a hint what I would do. Okay. Basically, this omega right here, this omega, this is a curly W omega. Hey, what's the units for omega? Radians per second, right? Because like how fast is the turn? Here, let me give you guys a visual. Okay, you guys remember these turntables? Here, we'll break up the turntables later this week to do like a friction lab. Isn't friction the force that's actually holding these outer points on? Okay. So if I wanted like turns per time, you guys ever heard of RPM? Guys, what does RPM stand for? Revolutions per minute. Yeah, which is not really a unit that we use in this class, but it is a good concept, isn't it? Revolutions per minute. Isn't that like turns compared to time? Turns per time? Right? Now, guys, we're not using revolutions per minute in this class. We're using what for what? Radians per second. Exactly. Radians per second. Huh. I would probably chase down that value first. And different ways to do it. But if I want to chase down this omega first, can you guys think of a way to get how many radians per second? Who can think of a way to do that? I don't look like physics. Go away, everything that's not physics. Only physics. Only physics. I'm the Ooh. I don't look like physics. Who can think of a way to figure out how could you quantify how fast this is rotating? Okay. You could kind of make headway that way. Circumference. All right. Let's chase on that too. That might initially be helpful. Maybe. Guys, how could you figure out what is the circumference? 2 pi r. Right. And actually, we do know r. Here, I'll make this capital R. Okay. Because that's this right here, isn't it? So this is like 38 meters. Okay. Now let's get a decimal value for here. 2 pi times 38. So I'm looking at about 238.8 maybe, if I round to the nearest 10. It'd be 238.8 meters. Okay, that might be helpful. Maybe I'll hang on to that. Okay, so that's how far it is all the way around. What else can you guys think? Hmm. Give you guys a hint. Okay. At this moment, the fact that you guys picked circumference, now you're one step away from either figuring out omega or v. You got kind of a choice. You could chase down either one of these to get these in one step. Well, either one of them in one step. Can you think of it either way to get omega or a way to get v? How could you do that? Huh? Huh. Huh. I'll go back to Mega because I was trying to kind of lead you guys down that way anyway. Okay. So you guys say this is radians per second? Okay. Well, guys, doesn't this time period correspond to one revolution? Okay. You guys, one revolution, how many radians is that equal to? 2 pi. Aha. So, here, hold on, this might be helpful later. Okay. Can I say that omega, the I'll spell this out, angular velocity is equal to 2 pi radians divided by the time period of 1200 seconds. Hey, look, that would give me radians per second. Right? I can tell how fast it's rotating. You guys get that? Right. Radians per second. Let's get a number on there. Let's do 2 pi radians, which is 1 revolution, of course, divided by 1200 seconds it takes to go all the way around. Right? So very, very, very slowly. I'm looking at 0.0052, and that would be here, I'll throw in one more digit. How about 4? Right, and that could be radians per second. So at least I'm working with 3 digits. Okay. Right. In fact, it takes a whole 20 minutes to go all the way around. Like if you were watching this, you might barely be able to see it moving with your eyes because it would take 20 minutes to go all the way around. Right? Just going that many radians per second. Okay. Right. Actually, that's one of the answers. That's this omega right here. So that's one answer. All right. Ooh, hey, guys, if you know how fast it's rotating, and you know how far you're out from the center, can you figure out your linear speed? Right? Like as if you were moving in straight lines, right? Moving straight lines. Guys, how do you go from omega to v? What do you have to do?
Omega times.
Ah, multiply by r. Ah, omega times r. That could give you v, right? Right? For radians per second times some radial size. That gives me how many? Oh, meters per second. Ooh. Right. So let's try that. Let's go. I know that v is equal to omega r. Okay. And for omega, well, we found that right here. That's the 0.00524. It's radians per second. And for radius, we found that earlier. Wasn't that 38 meters? You guys remember that? 38 meters. So put it all together. We're going to get, so this number right here times 38 is 0.199. 0.199. And what's the units on that number? 0.9199 what? Meters per second. Aha, because that's a linear speed. This is v right here. V equals. Is that it? Okay. So maybe about 0.2 meters per second. Okay. Pretty slow. Okay. That's definitely less than 1 mile per hour. It's going around real slow around this Ferris wheel. By the way, there's a different way you could have also gotten that number, playing off the. Remember earlier, you guys said, "Hey, what about circumference?" When we figured that out real fast. Is it also true that you travel this linear distance in this time interval? What do you think I'm going to get if I divide this many meters by this many seconds? Should I get this many meters per second? Let's put physics to the test. Let's see. We're going to find out. Oh, you write it down. I'll say v. Here's a different way to get v. Circumference divided by time period. So should be 238.8 meters in 1200 seconds. Let's see if I get the same linear speed. 238.8 over 1200. Oh yeah! Oh yeah! Look at that. Meters per second. It's the same thing. See how physics is all self-consistent? There's different paths through the forest, but all lead you to the same spot, as long as you're doing everything correctly. Right, you guys get that? Right, you could have done that from the outset. Right, so there's 2 different ways to get there for the linear speed. Right, so we got omega and radians per second, check. We got v in meters per second, check. Right. One last goal. What is the sort of like centripetal acceleration? Centripetal acceleration. That brings us back to these two. Right. There's 2 different ways to do it. Right. There's a linear speed way to do it in my left hand, and there's an angular speed way to do it in my right hand. Right. Here, this formula or this formula. Let's try it both ways. I bet they're the same value. You guys think they're the same value? Okay, let's find out. So let's go through angular speed first. So I'll say centripetal acceleration could be omega squared times r, which is, okay, here's my omega, 0.00524. That's radians per second. Okay, I'm going to square that value and then multiply by the radius of 38 meters. So that gives me, this is a sub c equals, let's see what's this, 0.0000524 squared times 38. I'm looking at, that's an extremely small value. Okay. 0.0000104. That's meters per second squared. Can it possibly be reasonable to write that in scientific notation? That's a lot of zeros. Yes, how can you write that in scientific notation?
1.04 times 10 to the
Negative.
negative.
Aha, exactly. Yeah, move the decimal here. So 1 point something. Okay. Times 10 to the negative 5. That's still meters per second squared. Yeah, that's the same value in scientific notation, isn't it? Yeah. Okay, just get rid of all the zero out like. Okay. And finally, let's tackle this from a linear speed point of view, which this one right here. Okay. So we're still getting centripetal acceleration. We already know the answer. I'm just showing you guys this is going to work. V squared divided by r. Let's try it out. Okay, so centripetal acceleration could also be v squared divided by r, which is oh, here's my v. Okay. 0.199 meters per second. So I'm going to square that and divide by 38 meters. Okay. I wonder if I'm going to get the same thing. Same thing. You guys think it's going to be the same thing? Let's see. 0.199 squared divided by 38. Wait a minute. Why is that off by... Did I mess this up? 0.00. Hold on. I'm off by a factor of 100 somehow. We go back and check my omega. That's right. Okay, squared times 38 is... Oh, you know what? I don't know what happened. I must have typed this in wrong. Because I'm off by 2 decimal places here. Okay, let me go back. This number is not correct. It should be the decimals right here. So get rid of all this. Okay. This is not 10 to the minus 5. It's 10 to the minus 3. Okay. And if I typed that wrong or what happened? Okay. So the number's correct. Just the decimal place is off. Okay. So yeah, good thing we did it a different way. So you can actually check the answer. So 0.199 squared divided by 38.
Does that mean it's 1.04 times 10 to the negative?
Yeah, 2 to the minus 3. Yeah. Then, okay, now this is the exact same thing. 0.00104. That's meters per second squared. Okay, which is the same thing as that. Okay, so now we're all good. We're all back on track. All right, all good. So work way around the Ferris wheel there. Okay. Oh wait, what is this compared to Earth gravity? What is Earth gravity again? Meters per second squared? 9.8. Isn't this really tiny compared to that? Okay. So if you were on this Ferris wheel, would you even feel the effect of that circular motion?
No.
Yeah, probably not. Right? It seems so tiny. It takes 20 minutes for that thing to go all the way around. Yeah, you probably wouldn't even feel that. Okay. All right. What's next? Yeah, let's do another one of these. Okay. Do number 10. This one looks fun. Number 10. We got a 25-gram metal washer tied to a 60-centimeter long string, whirled around in a vertical circle. Hey, do you guys remember when I took that cup of water and I whirled it around in a vertical circle and the water didn't fall out? That sounds a lot like this. But now we got a washer. Constant speed of 6 meters per second. Oh, by the way, that's weird. For you guys, when you have a vertical circle like this, your natural assumption is that it's speeding up on the way down and slowing down on the way up. So for them to give you a constant speed is kind of weird, but I mean, if they do that, just run with it. Okay. Calculate the tension in the string at the bottom of the circle and at the top of the circle. Okay, so do that. This out of the way. So shuffle. Number 10. Okay, so we got this washer tied to a string. It's going around a circle 60 centimeters radius. Okay, so I'll say R equals 60 centimeters. Yeah, should I put that in meters? How many meters is that?
6,000 or no, 6 million.
Huh?
0.6 million.
Point this. Yeah, 0.60 meters. You can see that on a meter stick. Guys, isn't this meter stick 1 meter? This is 1 meter. All right, here's the 60 centimeter mark. Hey, isn't this like just over halfway on the meter stick? Oh, just over half. Yeah, that's about right. Okay, so we got that. It's on the circular path, so here I'll dash off the circular path, get the idea. Okay, so it's following this path, going all around. And it does have this, they're saying a constant speed, right? Kind of weird. assumption. Let's go 6 meters per second. Right. So that by the time the washer gets down here, right, its direction is always changing, but its speed is always 6 meters per second. Right. So I'm going to reiterate something I said earlier today, or just a minute ago, right? Which is if they did not specify that, would you assume that it's speeding up on the way down because gravity's pulling down?
Yeah.
And it'd be slowing down on the way up because again gravity's still pulling down. Right. All right. So we're just gonna run with these numbers though. Their question is what's the tension in the string at the top, and also what's the tension in the string at the bottom. So let's create some free body diagrams. You guys ready for a free body diagram? Here, I'll get the string going both ways. Right, so at the top and at the bottom. Right? So make 2 different free body diagrams, one for the top, one for the bottom. Right? Let's start with what's one force? What's one force?
Weight.
Yeah, weight. Okay. Guess is this washer down here have some weight pulling straight down? mg. Okay. And guys, what about the top? Is it the same weight? It's the same weight. Yeah. So draw the same looking vector. Call it mg. I think they told us the mass, didn't they?
Yeah.
Oh, they did. They listed it in grams. Grams. What's that about? So mass is equal to 25.0 grams. Okay. Guys, do I want grams as the base SI unit for mass? What do I want? Kilograms. All the numbers we're going to feed into the calculator, well, the masses have to be in kilograms. Because how many kilograms is this? It's kilos a factor of a what?
0.025.
There you go, 0.025. And that's kilograms. Okay. Guys, isn't it true? Kilo is like 3 decimal places because kilo is 1,000 or something. Right, kilo is 1,000. Right. Right. So, okay, so that's the number that we're gonna be able to feed into the calculator to make equations. Okay. Right. So let's go. Well, here, that's not all the forces though. We got to have some more forces. Guys, what's another force acting on this washer? How about tension? Now, at the very top, the tension pulls which way? Yeah, straight down. This is really the force is on the washer. So the tension is pulling this washer straight down. Now, I don't know how big that is compared to the weight, so I'm going to guess it's bigger. I'll call it F sub T. Okay. I'm going to avoid capital T because maybe capital T could be the time period or something weird. Okay. Guys, what about at the bottom? At the bottom, the tension pulls which way?
Up.
Yeah, straight up. Straight up. Okay. Which tension do you think is bigger? If you had to guess, do you think the tension is bigger at the top or at the bottom?
The same. Oh, no,
Or could they be the same? I guess that could be a third option. Right. Let's see, show hands. Show hands. Okay. So your 3 options are, is the tension at the top bigger? Is the tension when it's going to the bottom bigger? Or are these the same tension? How many guys think that when it's going across the top, it's going to be greater tension? Who thinks that? Who thinks when it's going to the bottom, it's going to be greater tension? Right. And who thinks it's the same tension? Right. Now, my guess is that it's going to be a greater tension when it's going through the bottom. Right. I think so. Right. And the reason I think that is because it has to pull opposite of the weight. So maybe we'll call this FT top and call this FT bottom. Okay. Because these vectors down at the bottom partially cancel out. These vectors top add together to create some centripetal force and acceleration. Right. Okay. So that's what I think is going on. Now, I think we could probably, well, we have a speed V and we have a mass. And we also have a radius of curvature, which is 0.6 meters. So is there enough information to, okay, let's do this. Can you calculate centripetal force? Centripetal force? Right? You guys, once you got centripetal force, would that be the combination of these forces acting together? The weight plus the tension? Is that? Oh, I remember what I forgot to do, right, is make the actual weight, because we can get a numerical value for weight. Like here's mass. Right? Here's mass in kilograms. If you multiply by 10 meters per second squared, I'm going to call G equal to 10 meters per second squared. Just keep it simple. Okay. Right. Then I can get the weight. So guys, how much does the washer weigh? Huh? 25 newtons. 0.25 newtons of weight. Right? And that's also true down here. 0.25 newtons of weight. right? Is that fair? Okay, so let's do this right here. It means so centripetal force equals mv squared over r. Okay, guys good? Uh, okay, now there is a top condition. There's also a bottom condition. Now let's start with the top and see what happens. So guys, if I'm looking at the top, I can express centripetal force in terms of the given forces, which there's only two of them. Okay, so what do I do with this weight and what do I do with this tension to make centripetal force? Do I add or subtract them from each other? Yeah, add them together. So the tension force at top, which I don't know yet because that's what we're solving for, plus the weight, which we do have a value for, right, that conspires together to create the centripetal force at the top. They're both pointed straight down. Right? The weight's always down, and the tension, well, also happens to be pulled down at that moment. Right? And that is equal to your mv squared over r. Right? So Ft top plus, okay, here, I'll pop in some values now. So I know this is 0.25 newtons equals, okay, then I have this mass here of 0.025 kg. The speed is 6 meters per second, and that's being squared. And it's all divided by radius, curvature, and we're using 0.6 meters. Okay? So everything's in base SI units. Okay, right, that's okay. Right, okay. Right, now, to get the answer to what's the tension at the top, all I have to do is subtract over the weight. You guys it? Okay. So the tension at the top is point. You guys go ahead and do this with me. So you guys got calculators here. 0.025 times 6 squared divided by 0.6. So that's that right there. Okay. Then subtract over this weight. Okay. And okay. Oh, okay. I've got the number off screen. Somebody tell me what they got on their calculator screen. What's the tension in the string at the top? 1.25. Oh yeah, 1.25 newtons. All right. And for the win. 1.25 newtons. Right? Okay. So it turned out this whole fraction expression was like 1.5 newtons. So you need 1.5 newtons acting as centripetal force. 0.25 of those are already provided by the weight. Therefore, you only need 1.25 more from the tension to complete the necessary centripetal force. You guys get that? Right, that okay? Okay. Right, but we still got to figure out what's the tension at the bottom. And I told you guys that I think this is even more tension. And it's all show of hands, and some of you guys thought that too, although had votes on all those, so we're going to find out for sure. So now we're going to go to the bottom. And I can use the same thought process, but the numbers will play out a little bit different. So centripetal force, yes, is mv squared over r. Okay, so we got that. That's the answer to a recent lab you guys had with Play-Doh canisters and things. Okay. Now this time, okay, centripetal force down here at the bottom. What should I do with these? The tension versus the weight? Add or subtract? They subtract from each other. See how they're pointed opposite directions? So before the top, they conspired together. Okay. But down here, we're doing tension force bottom, which is what we're solving for, minus the weight. And that results in some mv squared over r. Okay? Right, okay? All right. And now I can just pop the numbers in, do a little algebra, just add over this term, and you get the answer. Actually, you know what? I think I don't even need a calculator. You guys remember all this mv squared over r came out to 1.5? You guys remember that? Now if I subtract 0.25, I get 1.25. Okay. But if this is still, I said this still, here it comes out to 1.5 newtons, which it does because we ran that before. Okay. And you know the weight is 0.25 newtons. What's the force tension at the bottom of the circle? 1.75. That's newtons. 1.75 newtons. There you go. Yeah. Okay, so now you can make a comparison. So when this washer is going through the top of the circle, the tension is not as much as it is when the washer is going through the bottom. Okay. Right, and it's keeping a constant speed somehow, going all the way around. Right, you guys good? All right. So here, we knocked out both of these, which are circular motion type. All these are good questions. That's why I picked them out. Let's Oh, okay. Let's look at some gravitation questions. So the font changed a little bit. It's a different textbook. I'll play with it. Um, great. Great. Let's go real basic. How about number 11? So where you just plug numbers in. So number 11. Calculate the force exerted by Jupiter on its moon Europa and the force exerted by Europa back on Jupiter. The mass of Jupiter is this many kilograms, the mass of Europa is this many kilograms, and the distance center to center is this many kilometers. Huh. Right. So we get those numbers on paper, and then we start working with that. So number 11. Right, we got here. I'll draw Jupiter here. So, let's say we got Europa somewhere out here, okay. And the mass of Jupiter they gave as 1.9 times 10 to the 27, and that's kilograms. So that's already base SI unit for mass. So that's good. Right, Europa right here, I'll call mass little m for Europa. And that has mass 4.80 10 to the 22 kilograms. No, if I pause right there, let's look at those orders of magnitude 10 to the 27 compared to 10 to the 22. How many decimal places removed is that? 5. You see 5 decimal places? Okay. So that means that Jupiter is what about 10, like almost 10,000 times as massive, right, which is pretty crazy. Uh, there's another number I need right here, which is the center to center distance. So if you go from the center of the moon to the center of Jupiter, I'll call this R because I bet Europa is like revolving around like that. Now they listed this as 7.43 times 10 to the 8 kilometers. Okay, so you want to plug that number in a calculator to make calculations? No. Why? What's wrong with that?
The total distance one, radius.
Yeah, I don't want kilometers. I want what? Meters. Okay. It's how do you go from kilometers to meters? How many decimal places removed is that?
4. Would have been 3.
3. Ah! Okay. So this shouldn't be 10 to the 8 for meters. It should be 10 to the what?
5.
Yes, three decimal places you said, right?
That'd be 11.
11. Yeah, 11. Right.
Exactly.
Because there's like 1,000 meters in a kilometer. Right, so multiply by 1,000. So we're going, so it's still 7.43, but now it's 10 to the 11. That's meters. And that's a number we can feed into the calculator. Okay. Now, you do need something else to solve this. They did not explicitly type out here. Okay. I'll ask you guys. Yes, there's one more number you need to solve this. They didn't actually tell you. Do you guys know what other piece of information you need?
Gravity constant.
Gravity constant. Oh yeah. You guys remember Von Jolly? Right. So 6.67 times 10 to the negative 11. You guys remember that? Okay. That's Newton meter squared per kilogram squared per units.
Did
Right.
you say Bon Jovi?
Von Jolly.
Oh.
Yeah. Yeah. So the force between these two. Right, so we got Jupiter and the moon pulling on each other. Of course, is resulting in this orbital motion. Do you guys remember that it goes like? Did I show this one yet? You guys remember this?
Yeah.
GMM over R squared. So we got that's what we did. GMM over R squared. Right. Okay. It's time for a calculator test. I see you guys can plug this in your calculator. And this is some number of newtons, right? So I took the units out, just consolidated that as newtons at the end, because these are all base SI unit values. With that. All right, so I'll type it. You guys type it. Let's see if we can all get the same number. Well, let's see. I might be able to prop this up a little bit. Let's see here.
Is the first one to the negative 11?
Yeah, 10 to the negative 11. That's gravity constant.
Ah, syntax error. Nice.
Huh. Okay, so everybody take a shot at this. See if we all get the same thing.
The variable to the 22nd or the 32nd? Well, from 8 times 10. You know?
Okay, I got 6.67 times 10 to the negative 11. I got 1.9 times 10 to the 27. All right, fix that. I got 4.8 times 10 to the 22. Okay, checking my math. And divide by, and I have 7.43 times 10 to the 11, and that is squared. Okay. All right, I got the answer in my calculator. All right, who else got the answer? Yeah, what you got, Kay?
I got 1.118 times 10 to the 27.
Huh. I got something a little different. How about anybody else? What's it about? Yeah, right. Huh? Yeah, that's what I got too. Yeah, all right, I got what Anna got, so that's probably it. 1.1 times 10 to the 16. And that's Newton's. Yeah, I'll show you guys exactly how I typed it. So I started with an open parenthesis, do 6.67 times 10 caret negative 11. Then, on this calculator, if you do close parenthesis, open parenthesis, it knows to multiply. But not all calculators do, but this one does. 1.9 times 10 to the 27, close open. 4.8 times 10 to the 22, close, divide by, and then open. And it's really critically important that you open a parenthesis after you hit divide by, because this whole thing's being squared and there's stuff multiplied in here. So yeah, so you gotta get that. It's 7.43 times 10 to the 11, and that's all squared. Yeah. All right, so yeah, we're getting 1.10 times 10 to the 16 newtons. Okay. Not so much Jupiter's pulling on Europa. Okay. Okay, guys good?
So, 1.
Yeah. Okay, so test of, yeah, can you correctly type that in the calculator?
16.
Yeah, there actually were 2 questions, weren't there?
Yeah.
So it says, calculate the force exerted by Jupiter on its moon Europa, which is that one right there. Also, calculate the force exerted by Europa on Jupiter. Guys, does this moon Europa pull on Jupiter a little bit?
Yeah.
How much? The same. It's the exact same value. This is the answer to both questions. You guys remember Newton's third law of motion? For every force, there's an equal and opposite reactive force. Yeah. We got an equal and opposite reactive pair right here. Also, my poster version shows that too. Does this force look like this force? It's the same force. Same force. Right, now, different masses, yeah, different effects. Right. Jupiter doesn't hardly move. Europa revolves around. Right, let's see. Let me put another one here. All right, so that was a pretty fundamental warm up. Oh, I like this question. Let's do 19. Right, so this one's a little bit more critical thinking right here. So this one will be fun. Number 19. Suppose a spacecraft is orbiting 3.92 times 10 to the 5 meters above the surface of Mars. Above the surface. Notice it's not the center, it's above the surface. That'll be important. Hold on to calculate the magnitude of Mars's gravitational field and approximate acceleration due to gravity experienced by the spacecraft. And they give you the mass of Mars and the radius of Mars. Okay? So we've got some kind of orbital situation. Okay, so this is number 19. Okay? So I got Mars right here. We're watching. Actually, I would start reading the question here. I want to get this real fast. Right. When I first started reading it, I was thinking that this poster was going to be useful. Right. So let me do a little side thought right here. Okay, guys, this is not exactly the same thing, but it's sort of related. If you were looking through a telescope and you watched the moon orbiting a planet, and you could kind of figure out how far away it was and how much time it took to go around, do you think, in principle, you could calculate the mass of the planet? Could you do that? Yeah. Okay. So it's sort of like this, but not exactly. All right. So we got a moon out here, and they told you a couple of values. So they told you here's Mars. Okay. They told you the radius of Mars. I'll call this right here is R Mars equals 3.40 times 10 to the 6 meters. So it's like 3.4 million meters. And the distance, oh, you know what? The distance to the moon, actually, if I drew this to scale, its moon is actually like really close. I'm going to get rid of that. Okay? Guys, the distance from the moon to the surface, it says like 10 to the 5. So I'll call this D for distance. That's 3.92 times 10 to the 5. 10 to the 5 meters. Guys, what's 10 to the 5 compared to 10 to the 6? It's not like 1/10. Right? So whatever the radius is, if you have 1/10 of that, yeah, this moon is actually ordering like fairly close to the big scheme of things, isn't it? Yeah. Actually, that's kind of where we park a lot of satellites, so it's not crazy. But you also know mass of Mars they gave as 6.39 times 10 to the 23 kilograms. And you guys also know universal gravity constant, 6.67 times 10 to the negative 11 meters squared per kilogram squared. Okay. All right, so we've got all these numbers. So everything on there, what we'll treat as given values. Okay. So what is the approximate acceleration due to gravity? So basically, what's the gravity field right here? Okay. Do you guys think the gravity field way out here is going to be a little weaker than it is truly at the surface? Yeah, it's going to be a little weaker. Okay. So gravity field. All right, let's see if you guys can come up with this. Guys, can you guys come up with an expression for gravity field for this type scenario?
GM by Bosch.
Yeah. GM divided by I'm gonna say x squared, okay, for some distance, because I don't want to confuse it with the radius of the planet. It's a little different.
What if it's whole like the combined radius of the orbit and the
Yeah. It's kind of this total distance from the center of Mars to the center of the moon. Can I call that x?
Yeah.
Yeah, which is of course r plus d, like that. Okay. Let's figure out what is x. Let's figure that out. X is equal to r plus d, which is like 3.4 times 10 to the 6 meters plus 3.9 times 10 to the 5 meters. Like that. So 3.4 times 10 to the 6 plus 392 times 10 to the 5. Okay. Yeah, so I'm getting 3.79 times 10 to the 6. That's still meters. Right. So there's my x value. I can plug it right there. Okay. I'm going to fill in some numbers here. So the gravity field is 6.67 times 10 to the negative 11. Mass of Mars, 6.39 times 10 to the 23. And then all divided by x squared. That's 3.79 times 10 to the 6. That's all being squared. This is some number of meters per second squared. Isn't that what gravity field is in? Meters per second squared? Okay. So let's put it all together. Okay, so I'll type this. First of all, is there any question about where any of these numbers are coming from? Okay. So I'll type this. You guys type this. Okay, let's see if we can all communicate with the calculator. So open parentheses, 6.67. Okay. Now move this off screen and solve the rest of this. 10 to the negative 11. 639. 10 to the 23. Divided by 3.792. 10 to the 6 being squared. Okay. Yeah, okay, I got a number that definitely looks reasonable. Like, you guys know Earth gravity is 9.8 meters per second squared. You guys think that a smaller planet and a moon in orbit is going to be less than that? Right? Okay. Who's got the answer? Which guy?
yeah 9. I got 2.9.
Ah, that's what I got. All right, I got what Gavin got. 2.96 meters per second squared. Like that. Yeah. All right, so here, let me show you guys how I typed it in the rest of it. So open parentheses, 6.67 times 10 to the negative 11, close open. 6.39 times 10 to the 23, close divide by open. 3.79 times 10 to the 6, and then close square. So that'll give you that gravity field. Okay. Yeah, I wonder You know what? Okay, I've only got a couple minutes left. So if I had like 5 or 10 minutes left, you know what I would want to do next? I would want to know. I wonder how much time it takes to go all the way around. Uh, there could kind of be a link to this one, couldn't there? Because we know this R, we know the mass of the planet, so no gravity field. Yeah, do you think in principle you could rearrange this and solve for t time period? Okay. Or you could go through centripetal force. You could actually go through, well, where my centripetal force poster go? It's the one we had earlier today. All right, but yeah, we got about a minute left, so I'll hang that up right there. So knocked out a few of those.